If you printed out your YouTube watch history right now, it would likely be over 70,000 pages long.
Easily, yeah.
Like 59 megabytes of pure, messy, totally unstructured web code. And today, we're taking you on a journey to explore one developer's quest to turn that chaotic digital footprint into a perfectly organized AI brain.
Right.
So, welcome to the deep dive.
Yeah.
Our mission today is to look at this fascinating progression hidden inside a programming chat log. We are, exploring the evolution of a custom Python tool called the YouTube Watch Indexer.
Yes, specifically looking at its path to the final iteration, which they called version 6.
Exactly. And we're really looking at a textbook case here.
Absolutely. It is a perfectly documented case of the engineering lifecycle. You see a user with this massive data set and a very ambitious goal. They want to feed years of their own viewing habits into NotebookLM.
Right, to create a searchable conversational interface about their own learning history, which is super cool.
It is, but they go through the classic phases of software development to get there. Like, first you try to make it work. Then you try to make it incredibly fast.
And completely break it in the process.
Exactly. You break it entirely. Then you are forced to just stop, step back, and truly understand the shape of your data. And only then can you build the final model.
Okay, let's unpack this. Because the core problem of parsing personal data is, well, it's way more complicated than just hitting a standard convert button on a massive file.
Oh, for sure.
Before we even get into the struggles of, writing Python scripts to extract this information, we have to talk about why a custom tool was necessary in the first place. Like, you have a 59 megabyte HTML file from Google Takeout.
Yeah.
Why couldn't the user just upload that file directly into NotebookLM and say, hey, AI, summarize my watching habits?
Well, the user initially attempted that very route, actually. They tried converting the raw HTML file directly into a PDF.
Which makes sense, because that's a standard ingestion format for these AI tools.
Right, exactly. And the conversion itself worked, but the resulting document was over 7,000 pages long, and it was practically unusable.
Wait, unusable how?
Well, an HTML export of your YouTube history is not a clean, curated list of, technical tutorials. It contains every YouTube short you ever swiped past.
Oh, every single one.
Every music video you left playing in the background, all the advertisements, and massive amounts of repeated structural noise.
Just junk data, basically.
Yeah, exactly. But beyond just the sheer volume of noise, there's a fundamental mechanical issue with how AI ingestion engines process converted web files.
Okay.
When you convert HTML to a PDF, the conversion process basically flattens the web page. It preserves the readable text, so it will print the words Arduino PWM tutorial on the page.
Right.
But it completely strips out the underlying hyperlink metadata.
I see.
Because NotebookLM's engine analyzes semantic text to build its vector database, right? It doesn't operate like a web browser executing background code.
So it creates a massive blind spot.
Exactly. What's fascinating here is that the AI can read the visible title of the video, but the actual URL, the critical piece of data needed to ever find that video again, is just discarded during the conversion.
That's wild. So if a system encounters a standard hyperlink tag, it just extracts the anchor text and totally ignores the destination address.
Yep, it's gone.
It's like handing someone a picture of a street sign instead of giving them the actual GPS coordinates.
That's a perfect analogy.
Like, the AI can read the words on the sign. It knows there's a destination called Arduino tutorial somewhere out there.
Yeah.
But it has no underlying mechanical way to route you there because the URL itself was treated as disposable background scenery.
Precisely. And this realization completely shifted the requirements for the developer's tool. To get maximum utility out of an AI assistant, the data couldn't just be visually readable.
I had to be explicit.
Explicitly formatted in plain text, yeah. Instead of relying on embedded links, the AI needs to ingest a string that looks something like this. Topic, Arduino, followed by a pipe character separator.
Okay.
Title, Arduino PWM tutorial, pipe URL, and then the raw explicit web address written out entirely, and then followed by the exact date.
So you have to literally write out the coordinates. You are forcing that invisible metadata into bold, plain text so the machine can actually map the source material.
Exactly. This single formatting shift is what turns a messy, flattened PDF into a highly structured knowledge base.
Right, because then it allows you to ask the AI highly specific queries, like
Yeah.
asking it to summarize all the engineering content you consumed in a specific year.
Yes, and it has the exact URLs readily available right there in its context window to cite its sources.
So we know how the data needs to be formatted. The goal is clear. But before we write complex Python code to extract this from the massive HTML file, I have to ask the obvious data portability question here.
I think I know where you're going with this.
Like, why are we dealing with HTML at all? If you want clean, machine-readable data, you just use a JSON file, right?
You'd think so, yeah.
JSON is literally designed to be parsed by code. It bypasses all the visual formatting mess of web pages entirely.
JSON, or JavaScript Object Notation, would absolutely be the ideal format here. It provides clean, unambiguous key-value pairs. There are no web containers, no styling tags, just raw data.
Right.
And the AI assisting the user during this project actually suggested exactly that. It said, abandon the HTML parsing entirely and just grab the watchhistory.json file from the Google Takeout export.
And let me guess what happened, based on the fact that we are talking about a massive HTML parsing script today.
You can probably guess.
The user went into their Takeout folder, unzipped the archive, and realized Google didn't actually provide a JSON file for their watch history.
Total heartbreak in the directory folder. Yeah. Google Takeout offers JSON for many of its services, but for YouTube history, it often only provides an HTML file.
That is so frustrating.
The developer was completely trapped. They had to fight this massive, unstructured web document whether they wanted to or not.
You know, this highlights such a massive friction point in the modern web architecture.
If we connect this to the bigger picture, it really does.
Data exports provided by big tech platforms are overwhelmingly optimized for human readability. They want you to be able to double-click an exported file, have it open in Chrome, and see a familiar, visually formatted list.
Right.
They aren't optimizing for a developer trying to pipe that data into a local machine learning model.
Exactly. By prioritizing a human-readable visual layout, they introduce incredible complexity for machine parsing. An HTML file utilizes layers of nested structural tags.
Like div containers and span classes.
Yeah, and inline styling for channel icons. All these things visually organize the text, but structurally create an absolute labyrinth. Developers are forced to build highly resilient, complex extraction tools just to reclaim their own raw data.
Which brings us to the actual final boss of this project, the extraction.
Right.
How do we pull 58,000 specific URLs and titles out of a 59 megabyte labyrinth?
It's not easy.
And this leads us directly into a classic programmer's dilemma, the eternal trade-off between speed and accuracy. So let's look at version 1 of the tool, the tortoise, versus version 3, the hare.
Okay, so version 1, our tortoise, was built using a very popular Python library called Beautiful Soup. This library is designed specifically for parsing HTML, and it operates by building a document object model, or DOM.
Okay, a DOM.
Yeah. It treats the massive HTML file not as a continuous string of text, but as a colossal family tree of nodes.
Right, so to find one specific video entry, Beautiful Soup has to map the relationship of every parent tag and child tag across the entire document.
Exactly.
It has to load that entire 70,000-page structural tree into the computer's active memory, the RAM, all at once.
Yes. And because it understands the exact structural hierarchy of the HTML, it is flawlessly accurate. Version 1 scanned the file and established our baseline.
The ground truth numbers.
Right. It found exactly 58,055 watched videos. It also perfectly filtered the dataset, isolating exactly 35 videos containing the keyword Arduino.
Okay, so the extraction logic was completely sound. But loading a DOM tree of that magnitude into memory is computationally heavy. I imagine it was just excruciatingly slow to run.
Oh, it took several minutes to process the file every single time the script ran.
Minutes. Just to parse a text file.
Yeah. And if a developer wants to tweak their search parameters or adjust how the date string is formatted, waiting 3 minutes for a script to finish testing is a massive bottleneck.
Yeah, that would drive me crazy.
Right. So the natural engineering impulse is to optimize for speed.
Enter version 3, the hare.
Exactly. Version 3 abandoned the memory-heavy Beautiful Soup library entirely. Instead of loading the whole document into RAM, it utilized a streaming line-by-line parser using regular expressions, commonly known as regex.
We should probably clarify how regex operates mechanically for anyone listening who hasn't written code before.
Sure.
Regular expressions don't understand the concept of a web page or a DOM tree. Regex is essentially a high-speed find-and-replace tool operating purely on the shapes of characters.
Right. It rapidly scans text looking for a specific pattern like the literal string of letters, HTTPS, and grabs everything until it hits a quotation mark.
It has zero awareness of whether that text is inside a video container or a channel icon?
None. But by processing the file sequentially, one line at a time, and dropping each line from memory as soon as it's read, version 3 was blindingly fast.
Like how fast?
We are talking mere seconds to process the entire file, tearing through thousands of videos per second.
Wait, okay. If regex is just scanning text line by line incredibly fast, looking for URLs, it should theoretically catch everything.
You'd think so.
But looking at the developer logs, version 3 only found 59 videos in total out of 58,000.
Yeah.
And it found 0 videos for the keyword Arduino. Like if it missed 99.9% of the dataset, that implies the target text isn't actually sitting neatly on a single line.
That's exactly the issue. The video link, the title text, and the timestamp must be heavily fractured. Version 3 was written with the assumption that a single watched video event would occupy a single continuous string of text.
Which makes sense logically if you're just thinking about a list.
Right. But Google Takeout's HTML is deeply nested. The hyperlink tag might exist on line 400, the video title on line 402, and the date on line 405.
All wrapped in different visual containers.
Exactly. Because the fast regex parser was skimming so quickly, looking strictly for a pattern where all 3 data points coexisted on a single line, it simply failed to recognize the multi-line structure.
Oh, wow. It's like programming a robot to speed read a novel, but instructing it to only register sentences that fit perfectly on one printed line.
That's a great way to put it.
It will finish the book in 2 seconds, but it will fail to comprehend a single paragraph.
Right. Skimming for speed resulted in complete data blindness. But compounding the structural failure was a fascinating dataset red herring that deeply confused the developer during the testing phase.
Wait, a red herring? Don't tell me they were pointing their optimized high-speed code at a completely empty file just to issue those fast parsing times.
Not empty, but heavily truncated. Google Takeout's export process handles massive archives in really quirky ways. Alongside the massive 59 megabyte master history file, this system will sometimes generate a secondary watchhistory.html file that is less than 1 megabyte.
Oh no, let me guess. It only contains the most recent block of viewing activity.
Exactly. And the developer had inadvertently pointed version 3 at the tiny truncated file.
Oh man.
And that tiny file happened to contain exactly 59 videos.
No way.
Yeah. So version 3 wasn't just failing to read the multi-line structure of the massive file. The developer was actively debugging their extraction logic against a fragmented dataset.
It creates total false confidence when the output number perfectly matches the total contents of the wrong file.
Exactly. It was a perfect storm of a fragile, single-line parser meeting a fragmented, incomplete dataset.
That is brutal.
Mm-hmm.
But to highlight just how confusing parsing this particular HTML export can be, we need to jump back slightly in the chat logs and look at version 2.
Oh, right, version 2.
Because this was an intermediate attempt to speed things up before they tried the line-by-line regex approach. And version 2 yielded some hilariously inflated results.
Yeah.
Let's call this the triple counting illusion.
Version 2 took a much simpler logical approach. The developer reasoned, instead of loading the complex DOM tree or writing complex multi-line regex patterns, let's just use a fast parser to find and count every single HTML hyperlink tag, every A tag in the entire document.
If we count the links, we count the videos.
That was the logic.
Here's where it gets really interesting. You look at the logs for version 2, and the tool claimed the user had watched 174,087 videos.
Yeah.
Let me do the math on that really quick. If the baseline from our accurate version 1 was roughly 58,000 videos and version 2 claims 174,000.
It's exactly 3 times as many.
Exactly 3. And our baseline of 35 Arduino videos mysteriously became 105. It's a perfect multiple of 3 across the board.
Yep.
The code isn't hallucinating random numbers. It's mechanically capturing 3 distinct elements for every single video watched. Did the user suddenly binge watch 3 times as many Arduino videos in their sleep?
Obviously not. It comes down to understanding the visual architecture of the Google Takeout export. When you open that HTML file in a browser, a single watched entry isn't just a simple text link, it's a structured block.
Okay, so the code is doing exactly what it was told to do, but the instruction itself was flawed. What are the 3 links making up a single entry?
Well, first you have the main thumbnail link, which points directly to the video URL.
Makes sense.
Immediately adjacent to that, usually formatted as smaller text, is a link to the creator's channel page.
Okay, that's 2.
And frequently, there is a third hyperlink embedded in the visual layout, sometimes linking to the YouTube homepage or some other navigation element.
Ah, and because version 2 was blindly counting every hyperlink tag it encountered, it counted the video, the channel, and the navigation element as 3 separate watched events.
Exactly. The extraction tool was accurately parsing the raw HTML code, but it fundamentally misunderstood what those code blocks represented in reality.
So the developer at this stage is facing a massive wall. They ran version 1 and got 58,000, but it was too slow.
Right.
They ran version 2 and got 174,000. They ran version 3 against a truncated file and got 59.
The JSON exit strategy is non-existent.
Brute force memory parsing with a DOM tree is too slow, and fast line-by-line skimming misses the multi-line architecture. So how do they finally solve this 70,000-page puzzle?
Well, they had to fundamentally alter their mental model of the dataset. They couldn't treat it as a massive memory-heavy tree, and they couldn't treat it as a series of isolated single lines.
Right.
This leads us to the masterpiece fix, version 3.3, which eventually evolved into the core processing engine of the final V6 product.
Okay, how did V6 pull it off?
The solution was a block-based state machine parser.
A state machine parser.
Yeah. Instead of analyzing the entire document structure all at once, or reading single lines in total isolation, the new streaming parser reads the file sequentially, but operates using conditional logic blocks.
Okay, so it maintains the speed of a streaming parser because it doesn't load the DOM into RAM, but it somehow gains the accuracy of context. How does it identify a block?
It scans the raw text incredibly fast until it detects a highly specific anchor word. In the context of this HTML file, every new video entry begins near the word watched.
Capital W, watched.
Exactly. When the parser hits that exact string, it flips an internal switch. The script essentially says, I am now actively inside a multi-line data block, and it begins temporarily capturing the lines of code that immediately follow.
Oh, that's brilliant. It groups the heavily fractured multi-line entry together into a temporary, manageable chunk.
Yes. And once it has established that active block, it applies a very strict rule to solve the triple counting bug from version 2. It scans the temporary block and captures only the first valid YouTube link it finds. It intentionally ignores the channel link and the navigation link that follow it.
Wow. It captures the core video URL, grabs the associated title text, and isolates the timestamp.
Correct.
And once it has collected those 3 distinct pieces of data, it formats them into our explicit plain text string, saves the output, closes the block, and resumes its high-speed scanning for the next instance of the word watched.
It's a highly elegant synthesis. It leverages the raw speed of sequential reading while maintaining structural awareness through those anchor words.
It is entirely akin to reading a massive reference manual. Like version 1 read every single word in the book, cover to cover, agonizing over the grammatical structure of every sentence, which took forever.
Yeah.
Version 3 just blindly scanned the margins looking for bullet points and missed all the actual text.
Exactly.
But version 6 operates by checking the formatting, finding the specific chapter headings, and isolating only the exact paragraphs required.
That is a perfect way to summarize it. And the operational metrics of version 6 demonstrate just how effective this architecture is. It accurately hits the verified roughly 58,000 video baseline.
Nice.
It correctly isolates the 35 Arduino videos. It outputs beautifully formatted, explicit plain text strings, perfectly optimized for NotebookLM ingestion.
Which was the whole goal.
Right. It also features secondary capabilities, like generating a CSV export for spreadsheet analysis, and it features a built-in search UI for immediate querying.
And crucially, it parses that entire 59 megabyte file in just 15 to 30 seconds.
Yeah, that is processing roughly 2,000 videos per second.
That is incredible. The tool evolved from a slow, computationally heavy script through a phase of buggy, hyperfast iterations into what the developer's chat log aptly categorizes as a personal YouTube knowledge indexing system.
It really is a system at that point.
So what does this all mean? When we zoom out from the specific Python libraries and the mechanics of HTML tags, this deep dive really serves as a masterclass in the software engineering lifecycle.
It absolutely does.
Like we witnessed phase 1, make it work, prioritizing accuracy over efficiency. We saw phase 2, try to make it fast, which inevitably breaks the system by making false assumptions about single-line data structures.
Right.
Phase 3 forces the critical step of analyzing the actual architecture of the raw material, realizing the data is heavily nested across multiple lines, and recognizing that weird triple-link structure of human-readable web exports.
And finally, phase 4. Fixing the logic model by building a block-based parser that respects the reality of the data. It demonstrates the significant effort required to simply reclaim and structure our own digital footprints. Data portability is often touted as a feature of the modern web, but as we saw with the lack of a standardized JSON export, Possessing a massive file is very different from actually wielding that data.
Exactly. But the underlying narrative is incredibly empowering. It shows how powerful it is to take control of your own unstructured data and actively mold it for modern AI tools.
Right.
You aren't just relying on whatever predictive algorithm a tech company feeds you on a homepage. By structuring your own archives, you can build a customized, highly specific, searchable brain of your own past learning.
It is empowering, yet it also raises a profound question regarding the trajectory of consumer technology.
Wow. Like what?
Well, if extracting, cleaning, and formatting our own personal data is this complex, this structurally messy, and this prone to triple counting errors for a human actively designing customized code, what does that imply for the future of automated AI personal assistants?
Oh, wow. That's a great point.
Right. When major tech platforms promise that their integrated AI will seamlessly read your context and automatically comprehend your digital life, will those systems truly understand the architecture of our data? Or will they just be quietly triple counting our habits behind the scenes, making false assumptions because the underlying web infrastructure remains fundamentally optimized for visual rendering rather than machine comprehension?
A future where our automated assistants confidently hallucinate that we've watched 3 times as many technical tutorials as we actually have, all because they misread a hidden channel link.
Precisely.
Well, that is definitely something to chew on. We want to thank you for joining us on this deep dive into the engineering lifecycle. We highly encourage you to go request your own data exports from your most used platforms. Open those files, look closely at the raw code, and see just how messy, nested, and chaotic your digital footprint really is. It is an illuminating look at the structures governing our online lives. Until next time.